What if I told you that by really, truly understanding just one core concept, you could solve a massive number of strength of materials MCQs without ever reaching for your calculator? Well, that concept is the Centroid, and today we're going to master it together. Hello, champions. Welcome back to Crack Civil with AI, your ultimate weapon to crack TNPSC AE, SSC JE, RRB JE, GATE, and ESC with smart, AI-powered explanations. Now, if you're new here or you just haven't gotten around to it yet, do me a favor and hit that red subscribe button right now. Press the bell icon and turn on all notifications. Why? So you never miss a single one of these high-yield lectures that could literally change your rank.
Okay, let's jump right in. Here's our game plan for today. We're going to start with the absolute basics. What even is a centroid? Then, and this is the important part, we'll build a powerful intuition for how it moves around. We'll look at what happens when you add area, what happens when you take it away with holes, and then we'll get into the math, locating it with coordinates, memorizing the must-know formulas, and finally, we'll tackle some tricky advanced cases you'll definitely see on your exams. Let's do this.
All right, first things first, we have to build a solid foundation. So let's start with the most fundamental question of all. So, what in the world is a centroid? Well, put simply, it's the one single point that acts as the geometric center for an entire area. You can think of it like this. Imagine a huge, sprawling city. The city center is like its centroid. It's the single point that represents the whole area. For our purposes in engineering, it's the point of balance, the spot where we can pretend the entire area is concentrated.
Now, here's the very first rule you need to burn into your memory. It's a big one. If a shape has an axis of symmetry, a line where you could fold it in half and the two sides would match up perfectly, then the centroid must lie somewhere on that line. It has no choice. Take a basic rectangle. You can draw a line right down the middle, vertically. That's an axis of symmetry. So we know for a fact the centroid is somewhere on that line.
Okay, so that makes sense. One axis of symmetry locks the centroid onto a line. But what if a shape has two axes of symmetry? Think about our rectangle again. It has a vertical one and it also has a horizontal one. So where's the centroid now? Well, it's exactly where you think it would be, right at the point where those two lines cross. That's why for a perfect circle or a rectangle, finding the centroid is a piece of cake. It's literally in the dead center.
All right, now we're getting to the most important part of this whole session. Seriously, if you can build an intuition for what we're about to cover, you'll be able to solve so many MCQs just by looking at them. We're going to figure out how the centroid moves when we start changing the shape.
Let's start with our baseline, our control subject, a simple, boring rectangle with a height of, let's say, h. Because it's perfectly symmetrical, we know its centroid is sitting comfortably right at the mid-height, at h divided by 2. It's perfectly balanced.
Okay, now let's mess with it. What if we take that rectangle and we weld another piece on top, turning it into a T-section? The total height is still h. So here's the million-dollar question. Does the centroid just stay put at that old midpoint of h over 2? What does your gut tell you?
No way! Of course not. The whole balance of the shape has changed. We've packed more area, more weight into the top half. That old center point at h over 2 isn't the true center anymore. And this leads us to the golden rule of this topic. The centroid is always attracted to the area. It gets pulled towards the heavier part. So for our T-section, the centroid has to shift up to a point somewhere above that old mid-height line. And this slide just makes it crystal clear. Look at the upright T-section on the left. Most of the area is up top, so the centroid shifts up. Now, what happens if we just flip it upside down to make an inverted T? The logic is exactly the same, just in reverse. Now the bulk of the area is at the bottom, so the centroid gets pulled down below the mid-height. You see? The centroid always follows the mass.
So what would it take to get the centroid back to the middle? Balance. It's all about balance. Look at a symmetrical eye section. The extra area we added at the top, the flange, is perfectly canceled out by an identical flange at the bottom. It's like a perfectly balanced tug of war. Since the top and bottom are pulling equally, the centroid stays exactly where it started, right at the mid-height.
Okay, we've seen what happens when we add area. But what about the opposite? This is a super common exam scenario. What happens when we subtract area by cutting a hole in something?
Let's look at this like a real MCQ. You've got a rectangle, 600 millimeters high. Before we do anything, its centroid is at the middle, right? Y equals 300 millimeters. Now, we come along and we cut a hole out of the upper half. So where is the new centroid? Is it still at 300? Does it go up or does it go down?
This is a classic example of where you can use pure logic to beat the exam.
No formulas needed. Let's just think it through. Step 1. What did we do? We removed area from the top. Step 2. So, what's the new situation? Well, the bottom half is now relatively heavier, or has more area, than the top half. Step 3. Apply our golden rule. The centroid moves towards the area. So where's the most area now? The bottom. Conclusion? The centroid has to shift downwards.
And there you have it. The correct answer has to be that y is less than 300 millimeters. This is exactly why building that intuition is so powerful. In a high-pressure exam where every second counts, being able to just look at a problem and eliminate the wrong answers is an absolute superpower. All right, we've got the intuition down. Now let's add a layer of precision and talk about how we actually define the centroid's location with math using coordinates. It's actually really simple. We use two coordinates you're already familiar with, x bar and y bar. All x bar is the horizontal distance from some vertical reference line, our y-axis. And y bar is just the vertical distance from a horizontal reference line, our x-axis. These two values, x bar, y bar, are basically the exact street address of our centroid. Now listen up, because this is a major pro tip for your exams. Technically, you can put your reference axis anywhere you want, but the smart way, the convention, is to always place the x-axis along the very bottom of your shape and the y-axis along the very left edge. Why do we do this? It's a simple trick to make our calculations foolproof. By doing this, our entire shape is in the first quadrant, meaning all our x and y values will be positive. This one little habit can save you from making silly and costly sign errors.
Okay, time to talk formulas. While that intuition is fantastic for multiple choice questions, when you need a precise numerical answer, you have to know these formulas by heart.
These are the big three you'll see over and over. For a rectangle with height h, y bar from the base is just h over 2. Easy, it's symmetrical. For a triangle, it's much lower down, at h over 3 from the base. And that makes perfect sense, right? A triangle is all wide at the bottom and pointing at the top, so the area concentration pulls the centroid down. Same idea for a semicircle. It's wide and flat on the bottom, so its centroid is also down low. The formula for that one is 4 times the radius divided by 3 pi.
And hey, speaking of that semicircle formula, you might want to make a special note of this number, 0.4244r. That's what 4 divided by 3 pi works out to. I'm telling you, this exact decimal shows up all the time in MCQ options, and if you can recognize it instantly, you can save yourself a calculation. Okay, let's push this a little further. Let's look at a slightly more advanced idea, one that feels a little weird at first, but makes total sense once you see it.
So here's a question to noodle on. Think about a C-channel, or a hollow tube, or a donut shape. Is it possible for the centroid, the geometric center of the material, to be located in a spot where there isn't any material at all, like in the empty space?
And the answer is absolutely yes. This is a really important concept for any kind of hollow or open section. Take a look at this hollow rectangle. A perfectly centered hole was cut out of it. Because the cut was concentric, the shape is still perfectly symmetrical both horizontally and vertically. And where's the centroid? It's still at the intersection of those two axes of symmetry. Even though that point is now in thin air, it is still the true point of geometric balance for all the material around it.
So if you only remember one single thing from our entire discussion today, please let it be this. This is the ultimate rule. The centroid always moves towards the side with more area, and it moves away from the side where area is taken away. If you can internalize that one sentence, you've pretty much mastered the concept for your exams. All right, if this deep dive really helped you finally get this concept, please do me a huge favor and smash that like button. It honestly gives me a huge boost to keep making more of these for you. And drop a comment below. What was your biggest doubt, or what topic do you want me to break down next? I read them all and I'll add it to the list. And of course, share this with your friends who are also preparing. Let's help everyone crack these exams together. And remember, consistency is what beats raw talent. Keep watching, keep practicing a little bit every day. You absolutely have got this. I will see you in the next high-yield lecture. Jai Hind.
And I'll leave you with one final question to think about until next time. You now have the intuition for how the centroid moves, but how would you actually calculate the exact x bar and y bar for a totally unsymmetrical shape, like an L section? Give that some thought, because we're going to break down the exact method for that in our very next explainer.